Hey, how y'all doing?
I'm good, yourself.
Glad to hear that. Summertime is a bit of a rush if you think about it.
Yes, very much.
Happens very quickly. On the other hand, it's also fair to say, like I maybe mentioned on the first day of class, that because it's such a quick experience, if you are able to spend the time and focus on the content, you know, it does seem as though it may be less time total to learn the material as well. Let me rephrase that a little bit. I mentioned concentration camp calculus that they had at a different university that I taught at. Literally in 12 weeks, they did an entire year's worth of courses, sort of like 12 weeks to do what would normally take 30. That's time and a half. Actually two and a half times the regular speed. And so the students were just doing calculus literally all morning, doing lectures, and then go home and do homework, and then work on other things just to catch up. And they knew the material about as well at the end, even though they maybe put in less time total than if they'd stretched it out over 30 full weeks. So with all that in mind, I think the point of today is to tackle any questions that you have related to the final exam that's coming up. So maybe I'm going to start by sharing a screen, mentioning a couple administrative announcements, and then we'll move forward from there. Okay, should they be able to see my screen? Good. Yeah, show up at the test. Um, Unless there is some medical reason why you can't, or we've already talked about it. The Baker Building, the new tallest building on campus, it seems like. Ground floor, which you enter from the west side, and then you make a quick left, no, right turn after you go in on that west side, and it should be right over there. That's where I'll be for like 8 hours tomorrow. And so if you just show up like 10:30, we've got an hour or so for office hours. Actually 10:10 is when I'm starting. But then between 11:40 and 12:10, I'm going to take a half hour break so we can have some food. Our test will be from 12:10 till 2 p.m. in that location. So that's the plan. You know how to do those things. And I think today the point is we should go over the final exam review content. Or if I click my way into week 5C by way of review, it sort of has a set of reminders. Maybe I'll mention these, then tackle, I guess, administrative questions that you have, then subject matter questions. Then we'll go on into newish, not newish, reviewish stuff. One is, yeah, there you go. Number two is, yeah, we just mentioned that. Um, a little bit more detail. The final exam is like a little bit longer, 50% longer, but you'll have about twice as much time to do the test, giving you more time per question. Students who felt rushed on midterm exams don't report that on the final exam they felt rushed. Some of them did use Indeed or do use Indeed the full amount of time, but no one says at the end of the day, and I like totally felt completely rushed and I couldn't finish. Students will sometimes tell me I felt like I could have used some more time, but most indicate something like, and if you had given me more time, I don't know that I could have done dramatically better because my understanding is good, but it's not perfect. That's as it should be. Okay. If you pay attention to the summer 2023 and summer 2024 videos, ignore anything about grades, ignore anything about those particular term characteristics of their exams because it's not relevant. If you do bring a computer, you're welcome to use JMP. The data sets I'll provide to you in Canvas, that's all good. However, I've written an exam that some students never even open the data sets because they don't need to. That's sort of a good thing. You shouldn't need to use the data sets, uh, but some people prefer to because they like JMP as a tool better than they like Better than they like having it just be on paper. But some students work like paper is cool, and those students don't necessarily open the test. Last time I did this, about a third of the students didn't use GMP at all, and a third used GMP considerably, and that middling third used it a little bit to tackle some questions, but not all of them. So that's a good place for me to stop and say, do you have any questions about formatting or anything like that?
So as of right now,
Okay. So, two things that we could do. One of them is to sort of, I'll mention a few things by way of last thoughts, okay? And then the other thing that we could do is go over any questions you have from the sample final exam. And so, had you looked over the sample final exam and have particular questions from that? If so, let's do that first.
no, I was planning on doing that after this
Okay. Yeah, yeah.
class. Yeah,
And
yeah.
so I just want to let you know the summer 2023 video has again typically the best questions from that sample final exam. And so let's do a couple quick last thoughts first, and then I can answer any questions that you'd like me to from the sample final exam. But I don't have to, and it's up to you. So once you sort of like look through that while I'm talking about these last few thoughts. And this is just
Okay.
my attempt to list off things that matter to me. They should matter to you with regard to the test, and they should matter to you with regard to using this Stat 313 subject content into the future. Um, Here are the key ideas. And shoot, I list off one per chapter, it seems like. In chapter one, it's analysis variance. Chapter two, regression. Chapter 3, we introduced the concept of effects, which allowed us to then more easily have multiple explanatory variables. Chapter 4, sequential sums of squares was chapter 4. In chapter 5, we noted if you have a properly designed experiment, you don't really worry about sequential versus adjusted sums of squares. It just works out. In chapter 6, it's like, what if we're going to combine categorical and quantitative variables both into one general linear model? In chapter 7, it's like, what if we have the effect of one variable depending on the level of a different variable interactions? Chapter 9 is like, oh yeah, let's formally say how you would check residuals, something you've been doing all along. In chapter 10, we did a little bit more with designing experiments. In particular, what if you have quantitative factors, things that could be treated as a number or as a categorical group? You might want to prefer using them as numbers and not just fitting a linear trend, but fitting maybe a quadratic or a cubic, whatever you need to have a comparable fit overall to the categorical fit. And if we're able to do that, the worst case scenario is like it still fits the same way. Best case scenario, though, is we can eliminate some model degrees of freedom, reserving more degrees of freedom for error, but the fewer model degrees of freedom means ultimately higher F ratios. We're better able to spot stuff that we're looking for if we take that quantitative approach, that polynomial approach for these quantitative factors. And then in chapter 11, it's sort of like, oh, well, how would you choose which X's to use even? We talked about forward selection, backwards elimination, stepwise best subsets. There's two other oddball topics. Partial F test, which is literally mentioned in chapter 10, but I wanted to focus you on doing it in a different context a little bit earlier. Okay. And then finally, logistic regression from yesterday, where we said, well, what if your response variable is just categorical? You succeeded or you failed, you lived or you died. How would we handle all of what we've learned so far in the context of a categorical response variable? The answer is, oh, it just works. As long as you remember to say, we're modeling not the We're not modeling the actual y itself or the typical value of y. We're modeling the log of the odds, if you will, the log of the chance of success over the chance of failure, the log of the chance of death over the chance of survival. As long as we model it that way, again, things work out really nicely. That is the other sort of linear model that we sometimes talk about. Our linear model in our book talk about, well, we got a whole bunch of different X's, and some of them could be categorical. The general linear model, a different form of that, says, well, we can handle even situations where we have a response variable that's categorical. What do we do then? We can handle it. Our software will do it for us. Okay, so that is the quick overview, but maybe doing a couple review of the highlights, the things that I would hope a student would remember for the exam or for real life, yeah, are the following. In ANOVA, it's a categorical explanatory variable. We really want to know, do the means differ? And if they do differ, use that Tukey thing to determine which groups are different from which other groups. In chapter 2, we fit a trend line, if you will, a quantitative explanatory variable. We're really tackling the question, not are the means different, but does the mean depend on X? Is there a trend of sorts? And if the trend is a non-zero, a slope that is other than zero, it says the mean depends on X. Ideally, you could also interpret the slope as the typical change in Y for a 1 unit increase in the X variable. I want to toss in here one other thing. Hey, if you have a larger sample size, it turns out that your test statistic values, whether it's the ANOVA F ratio or the F for a regression, or perhaps even the test of a slope, the T statistic in regression, those tend to increase if the null hypothesis is false. If there is truly a relationship, more data allows us to be more likely to spot it. Here's a situation where I should probably say, just interrupt me if you got a question, because otherwise I'm likely to move on.
You can move on.
Yep, sounds good. In chapters 3 and 4, that general linear model, the key really is we've got our different style parameterizations. JMP uses the sum to zero style, okay? But if you want to compare to a reference group, you could do that with an indicator parameterization within JMP. You choose which group you want to be the group you compare to. Easy to do. In chapter 4, we really define sequential sums of squares as our way of trying to analyze things. And we have to pick the first X variable, and then the second, then the third, then the fourth. And as long as you put them in that ordering, we're really saying, is SS error going down enough by adding this new term at this stage that we like the new term? We get a sequential test, if you will. Those are all partial F tests, by the way. These sequential tests boil down into, do you want to add the new term? Controlling for that collection of others that we already have. And ultimately, we end up with an understanding of sequential sums of squares, and then that tells us, yeah, adjusted is probably the way you want to go. And it's JMP's default. It's the way we statisticians tend to typically say things. Controlling for everything else out there, does this term matter? Because that's really what you want to ask. Is this a variable which makes sense? Is this a variable that proves itself worth keeping? Correlated X variables, like we had with the poets and the legs data sets, they're worth remembering. Correlated X's as opposed to uncorrelated X's. We have to be maybe a little bit more careful. Again, I'm pausing pregnantly for a moment, and if you have a question, I'm sure you'll yell it out, but otherwise, I'm going to be moving on.
So the general linear model, it's like I understand it, but I think if I'm given a problem and I'm not told directly that I need to, base it off of that, like how can I identify when I need to
Yeah.
Is it just memorizing the formula or like,
Well, I'll say in the general linear model section, right? The key thing that we really ended up doing was saying, defining the effect of a factor, okay? And sum to zero was the style we're using. So anytime you have a categorical factor in an analysis, if you're using the general linear model, analyze fit model, if you will, you're not really comparing means anymore like we did with ANOVA. We're rather saying, is there an effect of this variable? Or are all of the effects equal to zero? The null hypothesis is invariably alpha 1 equals 0, alpha 2 is 0, alpha 3 is 0, alpha 4, alpha 5. They're all zeros. And if one of the groups has a much higher mean than do the others, or if one of the groups has values that tend to be well above the average trend line, then you would say there is an effect of group on your response. So I think I tried to answer that, but I would love it if you'd rephrase.
no, I think that makes sense. I think I'm good to move on.
Yeah, I think with the general linear model, it's not that there is an equation as much as there is a concept. We don't compare means anymore, but we rather say there is possibly an effect of what group you're in on the response variable.
Okay. I'll keep,
Yeah. Chapter 5, though, we're still studying effects, yeah, and our variables, we tend to have more than one explanatory variable, but because they're categorical, maybe blocking factors or a complex experiment where there's two separate treatment effects, we basically say as long as we have balance, you're home free. Because balance, in other words, the same number of data points for each treatment combination. So, like if we have our data on the four different roots, five different root stocks, and the four different scions, the above ground variants, that's 20 possible treatments. For each of those 20 possible treatments, we would have to have exactly one data point, or exactly two data points, or exactly three data points. And as long as you have the exact same number of data points for each treatment combination that's possible, you've got what we call balance. And balance will give you orthogonality, which means the adjusted and sequential sums of squares are the same, which means we no longer have to say things like controlling for the other x variables. This one is significant. We could just say, hey, here's an x that's significant. Here's a factor that matters. We could separately estimate the impacts of the rootstock effect and the impact of the scion or the clonal variant effect. We don't have to really saying controlling for rootstock, then clone matters. Okay. So in chapter 5, balanced design is what we want to get because it gives us the orthogonality, which gives us all the goodness.
I always confuse the which one was it? I remember reading it. It was like you can have orthogonality but not be balanced, or is it reversed?
Okay, so orthogonality and balance. Balance always gives orthogonality, and orthogonality gives us what we like. The adjusted and sequential sums of squares being the same. So if adjusted and sequential sums of squares are the same, you have at least orthogonality. You don't necessarily have balance. We could have orthogonality without balance. Typically you wouldn't, because typically you design an experiment to be balanced. But like we suggested in class, if the rootstock R Gloria, Rapidia Gloria, is truly viewed as the typical rootstock that people use around here in San Luis Obispo for Mourvedre grapes, okay, then maybe we're going to have twice as many Rapidia Gloria rootstock as each of the others. So instead of 1, 2, 3, 4, 5 rootstocks, as though we have 1, 2, 3, and 3, and 4, and 5, we have, if you will, six different. I shouldn't say six different. We have six literal physical roots. that we attach to each of the cyans. If you have two readings of Rapidia gloria for each reading of the other rootstocks, you don't have balance, but you still would have orthogonality as long as it's 1, 1, 2, 1, 1 for every single one of the clonal treatments. If you always have 1, 1, 2, 1, 1, 1, 1, 2, 1, 1, 1, 1, 2, 1, 1 as the number of rootstocks of each variety, as long as it's always the same ratio of Rapidia gloria to the other rootstocks, two of them for every one of each of the others, you would still have orthogonality. And so some people might be wondering, well, why would you ever want to do that? If you have the desire to compare with greater precision the other rootstock to Rapidia gloria, the standard rootstock, the increased sample size for that particular rootstock variant increases the precision when estimating the effect of each of those rootstocks, like 3309, compared to our gloria. And so you could have orthogonality and it'd be great and wonderful, even if you don't have balance. Again, our book doesn't emphasize that, but indeed it is a truth. So you want to follow up on that?
No, I think I understand it pretty well. Thank you.
Yeah, cool. Um, hey, chapter 7. What about chapter 7? We spent a lot of time on chapter 7. Why did we spend so much time on chapter 7? It's because there's lots of different types of interactions. If you have a categorical variable and a categorical, you could interact them as long as you have at least two data points for each treatment combination. This seems to be a good way to go. You can estimate the interactions as long as you have at least two data points per treatment combination. If you have only one data point per treatment combination, you literally don't have enough degrees of freedom to estimate the interaction effects. So we tend to say if you have enough data, we could estimate the interactions in the categorical case. Categorical quantitative, well, I'm sort of saying quantitative gives us a slope. Categorical means you got 1, 2, 3 slopes for the 1, 2, 3 groups. Each group gets you a new trend line. And in the quantitative categorical interaction, we have now also the slopes could be different for the different categories. Yeah, and that makes some sense. Slopes could be different for the different groups. The impact of an additional unit of fertilizer might be different on one species than another. The species that can thrive in very poor soil will probably not have much benefit at all from an extra unit of fertilizer, but see the species that really need rich soil, they're going to really benefit. So there's going to be a huge impact in the one species, a huge slope in the one species compared to in the other. Quantitative interactions, those are tough. We walked it through in the context of the corn yield and rainfall data. And eventually we said at the end of the day, more rainfall is good. Yeah, a steep slope initially, but over time, the slopes flattened out and the impact of an extra inch of rain ended up being pretty minimal. We saw no real dramatic benefit from more rain if we already had many years gone by. Later in the data set, irrigation probably said, yeah, it sort of matters how much rain you get in total, but we can artificially provide water to these corn plants. And so I guess there could even be a negative slope that if you put on too much water early and then get a deluge of rain, you can end up drowning the plants. And so typically early on, more rain is good, steep slope. Later on, it flattens out and maybe even gets negative because of the impact of year. Year changes the slope of the rainfall yield relationship. And if the slope is different in different years, you would say that's an interaction. We even went so far as to say if you have this thing called a self interaction, an interaction with X with itself, the slope of X depends on actually the value of X. That sounds like it could be a quadratic relationship, literally. That is a situation where the slope of the XY relationship is changing. Initially, it's maybe negative, levels out, and then gets positive, maybe a curve like that. Or maybe it starts out as positive and then ends up leveling out and getting negative. You could have a downwards cupped parabola. Either way, you would be able to fit that with a quantitative interaction. X interacted with itself, if you will. And so that's how we would often quickly check for, hey, is the relationship linear or not? We fit a quadratic or a cubic, and if the quadratic or cubic terms are non-zero, if they're statistically significantly differing from zero, you'd say, oh, the linear model we had earlier fit is not sufficient. We can look for curvature by looking for a quadratic term. Again, I am about moving on.
I do think if there's time towards the end, you can maybe just briefly go over one, or even if you just go over the coin yield one again, just to refresh a quantitative interaction because it's kind of tricky.
Yeah, so I think I only partially heard you, but what I think I heard you say was, could you look at that one more time? And what I'd love to do is to do that in the context of the example that seems to work really well for this class, and that is the corn yield and rainfall data. Are you okay with that particular example?
Yes, that's the one I asked for.
Yeah.
Perfect.
Well, I'm glad that even though I didn't hear you, you were thinking the exact same way that I was. Okay, and slowly, it's appearing. Okay, so I've got my data on the rainfall level, the yield of corn, and information about which year it was that we saw that data point. And walking through from the very beginning, I think with Graph Builder is a good way to sort of explore what's going on. And the corn yield, yeah, it seems to be along the x-axis sort of nicely. Rainfall seems like a good variable to put along the x-axis. Rainfall predicts yield, yeah. And I'm going to drag year over here and sort of say, let's make it a color. And you could see that early on in blue, there seems to be blue positive. Later on in red, it seems pretty flat, higher and flat. If yours an overlay, it would say, let me arbitrarily take a collection of years. Let's call it the early years blue, then the middling years, that now is red. And then later middling, green and purple, sort of flat. And then even the last few years, it's maybe even negative. So it does seem as though the slope starts out steep and then flattens out, then maybe gets negative. The slope is increasing. No, the slope is decreasing, and the intercept is increasing across the different years. I could go ahead and try the fit model, and here's how I would do it. Yield seems to depend on the rainfall level, yeah, and then the year. And I've got rainfall level here and year over here highlighted. I can cross those. And because I don't like the centering, I'm going to deselect the centered version. And the analysis we get is more details than I really want to deal with. Let's get rid of the things that maybe don't so much focus our attention on the right things. Here's where I would probably focus. Um, one of these. R squared, hey, that's pretty good. The F ratio says at least one of the terms in the model matters. Boom. If I go down into the effects tests, I would say controlling for year and rainfall year interaction. Rainfall seems significant. Cool. Yay. Controlling for rainfall and the rainfall year interaction. Year seems significant. Again, that's weird to control for the interaction. Year then seems to pan out. Okay, controlling for rainfall and year, separately having a relationship to the response. Is the relationship of rainfall to yield different across the years? Yes, that is a cleaner way of interpreting the hypothesis test. Adjusted is not so natural. So let's maybe go under estimates and talk about the sequential way we would approach it. I'd say, does rainfall matter? Yes, it does. Already controlling for rainfall, does year appear to help us? Yes, it does. And if we all have rainfall and year in the model, does rainfall is its relationship to yield? Does the slope depend on the year? Yes, it seems as though that's the case. So, because of the model complexity being increased by this second order term down here, I would say you need to have the simpler terms listed first, and perhaps sequential is a good way to go. If we want to talk about interpreting the slope of year, it's sort of awkward to interpret the slope of year, controlling for the year interaction with rainfall. Literally, I could try to do it, allowing for there to be a trend across the rainfall levels and allowing for the trend across the rainfall levels to be different in the different years. On average, is there a trend across the years? Reads a little bit hinky, a little bit off. Okay. The parameter estimates are what if we were wanting to put things into a profile expression. I think I'd just rather go into factor profiling, profiler. And literally, I can tackle these sort of questions by saying, okay, well, for early on, what is the rainfall yield relationship? Seems pretty steep. As we go on in time, it seems as though it flattens out or maybe even gets negative. Again, perhaps using too much irrigation, and then all of a sudden the clouds start dumping a lot of rain on you. That could extra rain could harm the corn. We also see that the intercept seems to be climbing while the slope is flattening. And even this average, I guess, value at the average rainfall amount, okay, the average value here, 24.49, across the years, it goes up to 30 and 31 and even 32 and 33 and 34. So at the typical rainfall level, the average amount of rainfall level, as you go from early to late, we do see the increase in then the typical amount of yield. So it allows us, the prediction profiler, to simply say, for different levels of one X, how does the other X relate to Y? What is the slope? So I think I emphasized a couple of the things that you were wanting to ask about, but I think a follow-up would be good if you'd want.
Yes. No, I think it was pretty straightforward. I understand it pretty well.
Yeah, and there's just so freaking much to know.
Yeah, there really is.
The thing is, I've been doing this stuff for, geez, I'm 60, since I've been like 25 or something, maybe even younger in some regards. And so it feels pretty comfortable to me, but learning this content in 313, it is a heavy lift. And in the summer, actually, in a regular term, in any one week, it's like, oh, okay, that's one concept. I can handle that. Or there's two concepts. I can handle those. In summer, it's like four concepts a week. And so it does get a little bit heavy. So I'm going to skip 8 and 9 because it's all about linearity, normality, equality of spread, things that we know how to do. But if you want to ask about anything in 9, I'm happy to answer.
No, I'm pretty comfortable with those. You can move on to 10, 11. I think 10, 11 was something I was struggling with a bit.
Yeah. 10 and 11 are where we put things together and say, well, we're got a piece over here, a piece over here. We learn this, we learn that, and let's put this all together. It's like once you learn how to do some basic things in cooking, then all of a sudden they ask you to sort of put them together, and it gets more challenging until you're really solid on it. The way to think about chapter 10 is, oh, we got a fancy experiment with more than just one factor or more than just two factors. We can deal with that. Okay. And so we have these main effects, check, interactions, sure, no problem. And in fact, you could even have, for quantitative X, we could have polynomial fits. And it turns out that usually that polynomial approach does pay off, that it allows us to fit with a simpler model than quadratic or cubic or quartic. We could fit with a simpler model the same trends as we could fit with a categorical factor. Indeed, increasing your typical F ratios for parameters, variables that you like to investigate. So we tend to like that approach if you have got quantitative factors, like the actual amount of fertilizer you apply. Just give me the number, treat it like X and put in X squared and we're all good. Okay. Um, so that's in 10. And we did a little bit of model checking there to see how things work. And one of the model checking things that we looked at was using Box-Cox transformation, literally y to the power of some number lambda. How do we pick the best lambda? Just let Box-Cox tell you. The minimum, okay, of that curve is the best lambda. And if the best lambda is something like 1, or could be 1, you don't transform. If the best lambda is 1/2 or close to 1/2, you'd say you take a root. If the best lambda was 0, you take a log. We're all good. Chapter 11 was a little more complex, though. In chapter 11, we had the problem of you didn't design an experiment, you simply collected a collection of X values on things that you think might be related to your response Y. So I'll give you an example. There was a grad student in biology who 20 some years ago was dropped off once a week over at the north end of, I guess, Morro Bay along the Sandspit and would walk down 3 miles to where she had parked her car in Montaña de Oro. And as she walked along the beach, every time she saw a plover nest, a snowy plover nest, she recorded and measured every detail about the nest, including, how wide it was, how close of a distance from the nest to the nearest piece of shade, how far above the tide line it was. Hundreds and hundreds and hundreds of variables. She was collecting these variables to try and figure out, does that relate to whether the nest hatched or not? So clearly it's logistic regression. Does the nest hatch or not? Do you get new plovers out of this nesting experience? And she tried to sort of tackle the question of which X's should I use in my analysis of the 30 some variables that she could have used to try to predict whether the plover's nest would hatch or not. She said, I need to explore. And the criterion we could use would be lowest AIC, and we tried best subsets and it identified about 6 variables that were pretty good at predicting whether the nest would hatch or not. Okay. And so we used the data. Best subsets is effectively a way of saying you had 30 variables. 2 to the power of 30 is the number of models you could try and fit. And that was so many models that there's no way anyone could ever do it. So we just said let's go ahead and algorithmically eliminate some of the variables which appear unhelpful and see if any of the others are helpful. And so after we worked it down to those 5 or 6 variables that mattered, we did some model checking and eventually published a paper on, oh, here's the things that matter with regard to snowy plover, whether they're going to hatch or not. And the nest choice of location is what she's trying to quantify. And how do certain nest locations benefit or drawback, the actual hatchlings that may or may not occur. So model selection, the key things are AIC is the thing to remember. Minimum AIC is best. Forward selection, well, just keep adding variables in. Add always the best one first. And then once you add it in the first, find out which one's the second one to add in by, which is the next biggest bang for your buck. Backwards elimination is going the other way, taking the largest possible model and eliminating variables one at a time that are not important. And neither of these will get you to guarantee the right answer. Okay. And like they say, 2 steps forward, 1 step back. Stepwise regression is probably better than either a forward or backwards. because it adds variables in, and then if at any stage a variable that you earlier had added in appears less helpful, you get rid of it. Again, 2 steps forward, 1 step back. We check at each step whether all of the variables we had previously added are worth keeping. Best subsets, keep them all, keep them all. Try every possible combination. Sometimes, however, that's so many possible combinations you can't do them all. After you do fit a collection of variables, okay, maybe then you're going to sort of look for any possible interactions or quadratics, etc. Maybe you'll say, oh, damn it, I needed to have rephrased y. I should do a natural log of y instead. And once we try something, if we go back to ground zero, it's sort of like going to the hardware store. If you are not from a family where there's a professional contractor, odds are you go to the hardware store and you buy the thing that you think will fix what you got. And you go home and then you discover, hold on, there's that other tool that they suggested I should use, but I didn't buy it because I thought maybe I didn't have to. Now I have to go back and buy the new tool. That's like what happens when we do our model checking. We say, oh, yeah, that was quadratic. Have to add in a quadratic term and then start over or go back to some earlier point in the process. And by refining the model, we end up with something that will give us ultimately answers to the questions that we really have. You want to follow up with either chapter 10 or 11 because I can.
A lot of information. I think I just need to go over it like on my own, just probably reread the chapters. But I don't have any questions so far.
Yeah. Like if I shout at you for 3 minutes and say, do you got any questions? It's mostly because sometimes a person will think, oh, yeah, what about best subsets again? Or, oh, yeah, how does stepwise really work again? Those questions that come up on the fly, I want to be sure to answer those. And if you don't have any right now, you know what? Hey, there's a video or two plus other things by way of resources available.
Yeah, if I have any questions, I'll
Yeah, love it. Last two things got to mention. One of them is that partial F test. And the partial F test is pretty darn important because it allows us to tackle some questions that can't easily be handled with a test of the whole model. A model utility test is at least one of the variables in the model helpful, or the test of individual variables. Sometimes, for example, if you have correlated X variables, you want to know, hey, are any of these variables overall helpful? Are any of the three helpful? And you could say, well, let's fit the complete model with all three X variables in it, plus another host of other X variables. And the alternative, the reduced model, if you will, I'm sorry, the complete model has all of the X variables in it. And that is your alternative hypothesis. The null hypothesis is your reduced model. Yeah, let's eliminate these three variables. It's sort of like in the air pollution and mortality data set. If we try the model with all the x's that aren't related to air quality, yeah, and then our that's our reduced model, and the complete model, we add in the three air quality variables as well. And are we fitting better? If SS error goes down by adding these new variables, maybe there's something in the variables that was helpful. Or if SS for the model increases by adding those three air pollutant variables, you'd say at least one of them was helpful. And so what we're really checking for is across the group of the three is at least one of them beneficial for us. And the reason we might want to check all three simultaneously is because they're correlated variables. When the sulfur dioxide level is high, then we have the hydrocarbon level being high and the nitrous oxide level is high. And if nitrous oxide level is low, then the other two are low. The three variables are pretty highly correlated. And so if you have at least one of them mattering, that says pollution matters. You don't have to tell me what aspect, what part, what particulate in the pollution does impact a person's length of life. If you're able to tell me pollution in general is important, the more polluted the air, the shorter the lives are, that's worth knowing. And so in the presence of correlated X variables, partial F tests are really pretty helpful. It will answer the question is at least one of them helping us? Even though we might not be able to tell you which one it is, we could tell you that at least one of them is helpful. Logistic regression, yeah, let's just redo everything we did. Everything we did. Except for on the left-hand side, you have the log, natural log, of the odds, the natural log of the chance of survival over the chance of death. And if I find the chance of survival over the chance of death and the natural log of that, that could be looking like on the right-hand side, any other general linear model. And we have a way of converting from any right-hand side, the intercept and the slopes and the effects. We have a way of converting into a chance of death. We could even plot those chances of death as a function of x, and we could even do it separately for different groups. I guess at a basic level, the tests are all of a sudden chi-square tests, not F tests. There you go. Categorical variables are effects on the log odds. Quantitative variables have a slope related to the log of the odds. Multiple variables, anything we've done in chapter 4 through 11, it all works the same. As long as we have on the left-hand side the chance of success surviving over the chance of dying, that is called the odds, and the log of that, the natural log of that, just works out brilliantly. If you got a quantitative x variable, no problem. Categorical x variable, no problem. You got both, no problem. It allows us to tackle situations where we have a y variable that is categorical. Any questions about either of these two?
Surprisingly, no. I think I'm okay.
Okay. I think the key is one thing at a time. It's easy for me to go through the list by shouting loud things really quickly, and you'd say, "Okay, yeah, partial F, got it," or AIC, I know what that is, or interaction between an X that's categorical and an X that's quantitative. Okay, yeah, I get different slopes for the different groups. One at a time, it's easy. It's when you put it all together that it becomes challenging. So I want to leave you with one thing. During the test, if you want me to rephrase any questions, do not hesitate to ask me to rephrase. Just walk right up and say, could you rephrase this problem? And I'll say, okay, let me rephrase. And that will make it dramatically quicker. And yeah, you can't say, hey, how do I do this problem? But what you can say is, can you rephrase it a second time or a third time? And I'm happy to rephrase problems many, many times because if you then say, yeah, I know what to do now, then that's a win. So tests should be learning experiences. I don't write a perfect test question. No one ever does. And I don't presume that I do. And because that rephrasing or a willingness to rephrase on my part is probably part of the learning experience that is a test. Okay, so that's it for me for the
Thank you so
moment. If you
much.
got any questions, I'm happy to answer them now for a couple minutes. Otherwise, I'm going to stop the share.
Yeah, I think I'm okay, but I would like to say thank you. I think you offering to rephrase test questions is very, very helpful. So thank you.
Yeah, not a problem. In fact, that is my default mode. It is just hard to do when you're all taking the test asynchronously. And so that's why one of the reasons why the in-person is really good for a final exam. So I'll see you tomorrow. Enjoy your day until then.
I'll see you tomorrow. Thank you so much.
Bye-bye.